All right, guys, it's here. What you've been waiting for. Part 2 of 4.3. We ended the last lecture talking about the first derivative test. And remember what the first derivative test told us. If we found the places where the first derivative is 0, those are our critical points, right? And possible max or mins. If we look at the first derivative, if it changes from positive to negative, we have a max at that point. If it changes from negative to positive, we have a min. So there are other ways that we can actually talk about how to find those max and mins with something called the second derivative test. But before we get to the second derivative test, well, because we said second derivative, let's talk kind of about what maybe the second derivative does or what it implies, right, in the graph of a function. So if I look at the graph of this function here and I decide, because why wouldn't I, to start taking my tangent lines, right? We know some things that are happening. So here I'm going to start switching to the outside. I'm just sketching my tangent lines here, kind of thinking about what the derivative is going to be doing, right? It looks like it's 0 for a while here, which is all right. And then starts going negative again. So we know, right, that from here, f primed is positive, right? We know from here to here, f primed is negative. And then from here, you know, this is pretty constant up here, but we'll just say from here to here, here to here, I guess, about f primed is positive. But what does the second derivative tell us? Well, remember the second derivative tells us the second derivative is the derivative of the first derivative. But look at what's happening here. So if you notice, the derivative tells us a rate of change. So the second derivative is going to talk about the rate of change of my first derivative. So let's look at what's happening to my first derivative right here. I have positive slopes, right? This is a pretty steep slope. Then as you notice, clearly I'm heading to 0, right? So I have positive slope, positive, positive, not quite as positive, so I'm gonna make those a little bit smaller. I hit 0 and then I get to negative, negative, even more negative, and then I start kind of getting less negative, right? Negative, then I hit to 0, positive, more positive, right? And getting steeper slopes until maybe right here, and my slopes are gonna start getting a little bit not quite as steep, still positive, right? But not quite as steep until it hits 0 and then I go negative again. So when we're talking about the second derivative, we're talking about rates of change of the derivative. From right about, I'd say from, anywhere over here until maybe right about here, what do you notice about the slopes of those tangent lines, right? They are decreasing. They were pretty steep. They're not getting as steep. They're going to 0, and then we're actually getting negative. So if you notice in this part of the graph right here, we would expect our second derivative to be less than 0. Why is that? Because f primed is decreasing. Ooh. Right? So if f primed, if the slope of my tangent lines are getting smaller, right, if they're decreasing, that tells me my second derivative then is negative. Same thing over here. Where did we kind of start changing? If we look at what's happening here at this point, right, what started happening? So my slopes started getting bigger. So they were really quite negative, and then they started flattening out a little bit, meaning we're going to bigger numbers, right, more positive numbers, to 0, and then we're getting more and more positive. So in this case, f primed is increasing, right? It's stopping going negative and it's starting to go back toward the positive direction. So what do I know about the second derivative here? That must be positive, because remember, we know the derivative tells us if whatever it is, it tells us if that thing is increasing or decreasing. Like your happiness right now is increasing, correct? Because you're watching this video. So that would mean that the derivative of your happiness is positive. Let's not talk about your happiness decreasing. I don't think that's possible when you're doing math. Anyway, and then now what do you notice here? So they're positive, but remember they're getting less positive now. You can see my positive signs kind of get a little smaller, go to 0, and then they're getting more and more negative, right? So they're decreasing. So the slope of the tangent lines is decreasing, so that means my derivative is decreasing. So what do we know then about our second derivative? It must be less than 0. So the second derivative is kind of a it is cool, of describing something on our graph that we call concavity. And concavity is kind of just what you think it would be. There's the word cave in it. That's how I think of it. And so concavity, basically, am I like pointing down or am I pointing up? So what we say here is that we are, in this case, right, where the second derivative is negative, we say we're concave down. Okay, so basically what we say is our slope, the tangent lines kind of sit above above the graph of the function, or another way of saying that is that it's decreasing. In this case right here, we're concave down, or excuse me, concave up. What we mean by concave up is the tangent lines are kind of sitting below the function and the function is kind of pointing up, right? I have like a smiley face, right? Concave up, this is concave down. And then clearly over here, this is concave down. So this is what we mean by concavity. And if you notice, concave down is going to correspond to a negative second derivative. Concave up is going to correspond to a positive second derivative. Okay, so that's the definition of concavity. Okay, another way to say that is if it's concave down, then the derivative is decreasing. If it's concave up, then the derivative is increasing. So the way this is going to be kind of stupid, but the way I remember it is if my second derivative is positive, I think of it in money terms. If I have a positive amount of money, positive amount of money in my checking account, I'm happy. If I have a negative amount of money in my checking account, I'm sad. I don't know why. That helps me think about if it's concave up or concave down. Okay. All right, you guys. So let's kind of state this a little bit more. Oh, and one other thing that is really cool that you're going to be really excited about is that this point right here, right, where we change from going concave down to concave up, this right here, this is where my second derivative would be equal to 0, right? Because I'm going from my second derivative being negative to my second derivative being positive. And this is what we call an inflection point. Now, it's not just where my second derivative is 0, it's also where we change concavity. So that's what we call an inflection point because I'm changing from going concave down to going concave up. So let's kind of define, let's put this all together because that was a little bit convoluted, but I hope you liked it. So let's look at the definition. So definition. So a couple things we need to have, right? We're taking derivatives. So let's make sure we can actually do that. So let's let f be differentiable on an open interval I. On an open interval I. All right, so here's how we're going to define this stuff. If the derivative is increasing on I, then what do we say? Then f, right, is concave up. So if the derivative is increasing on I, then f is concave up. And what does that mean? That means the second derivative, right, is greater than 0. 2, if the derivative is decreasing, right, those slopes of those tangent lines are getting smaller, right? They go from positive and then they go to negative or something like that. If f prime is decreasing on I, then f prime is decreasing. Then f is what we say concave down on I, right? And concave up, I'm just going to kind of put a little, in general, it looks like that, right? In general. I mean, it doesn't have to be that obvious. Sometimes you can have concavity that's even just real gentle concavity. I don't know what that means exactly. I'm not even going to keep going with that. All right, so concave down. And what is concave down? That's where my second derivative is 0. Or less than 0, right? So concave down has this kind of idea to it. And then one other definition, let's talk about inflection points. So really quick, if f, we got to say it's continuous, is continuous because I could change, well, I'll talk about that in a minute. Okay, so if f is continuous at some value c and f changes concavity at c, so that continuous part is actually pretty important. Concavity at C, that means either going, as you look from left to right, either going concave up to concave down or concave down to concave up, right? Then F has an inflection point. At C. So what does that mean also? That means that my second derivative either goes from positive to negative or negative to positive. Now, so we could have something like that, right? And then where would my inflection point would be right there. We could go from concave up to concave down. We could have something like this, and that would be my inflection point. One thing that we can't have, it's requiring that my function be continuous there. I'm gonna go over here a little bit. So you can have situations maybe where like 1 over x, right? 1 over x looks like this. So if you look at 1 over x, we're concave down over here and we're concave up over here. But, oh no, but I'm just gonna, there we go. But I don't actually have an inflection point at 0 because there's a vertical asymptote there. So even though I do change concavity, on each side of the y-axis, I can't actually say I have an inflection point at 0 because I'm not even defined at 0. So I can't even really say I change concavity at 0 because I'm not defined at 0. So does that make sense? I hope so. Let's look at a couple simple examples. All right, so I'm gonna get rid of that, although actually I probably could use it. But let's look at something like a function that I actually know. Well, let's get a couple. So find intervals of concavity, and inflection points for the following functions. Inflections points? Nope. All right. So let's look at something kind of simple for right now. So let's look at f of x equals x cubed minus 1. Okay, so f of x equals x cubed minus 1. So x cubed, we know what x cubed looks like, right? It's this kind of s-looking thing. And so x cubed minus 1 is just going to be that s-looking thing just shifted down 1. So if I put in, 0 for x, I get negative 1. If I put in 1 and negative 1, if I put in 1, I get 0. If I put in negative 1, I get negative 2. So the graph looks like this. And if I look at this graph, let's just talk about what we would expect to happen, right? If I look at this, look at what's happening to your slope of your tangent lines here. Eventually, right, my tangent lines go to 0. And then they start increasing again. So I would expect this function, right, to be concave down here. And then I would expect this function to be concave up here. And because I am defined at this point right here, I'm going to expect to get an inflection point there. So let's show me the calculus, people. Show me the calculus. So I need the calculus to verify that. So let's see what f primed is. So f primed is 3x squared. Why am I taking f primed? Because I need f primed to get to f double primed. F double primed then is 6x. So right now, you guys, I'm not asking for max and mins. I'm not asking for increasing and decreasing. So I don't actually need to set my first derivative equal to 0 because I don't really care. I don't really care about my first derivative right now. I'm just using my first derivative to get my second derivative. Now, how are we going to find intervals of concavity? Well, what do I know about where I'm concave down? I know that f double prime must be negative. Where do I know I'm concave up? F double prime must be positive. So if I want to find the spots, right, where I'm concave up or concave down, I know that in between here, either f double prime equals 0, excuse me, or f double primed is undefined, because we have to consider that situation like 1 over x, right? So let's see if we can find the places where my second derivative is 0. This is kind of like your critical points for your second derivative, or kind of like your critical. It's possible inflection points, let's say that. So I'm going to set this guy equal to 0. Obviously, the only thing that makes that 0 is 0. So just like I did with the first derivative, I'm going to test around my possible inflection point here. So I'm going to test into f double prime. So if I put in -1 times 6 is a -6. So this is negative. So I know my function is concave down. If I put in a positive number like 1 here, I know my function is concave up. I also know that that my function is continuous at 0, right? I can plug that in. So I've shown that that's an inflection point. And this sure is doing what we expected it to do, right? We have a negative to the left of 0. We know that's concave down, so that makes sense. We know this function is concave up to the right of 0. So it should look something like this. So how do I describe this? Well, I'm going to say it's concave up. I put C with an arrow up because I'm cool. Because that makes me cool. So C up, which is concave up. If you want to go impress your friends with that, you're welcome to do so. C down. Concave down is minus infinity to 0. Remember, negative in my checking account makes me sad. Positive in my checking account makes me happy. So I have 0 to infinity is concave up. Concave down is minus infinity to 0. And then do we have an inflection point? Sure enough, you have an inflection point. And I am a little picky on this. Surprise, surprise. When it says point, I would like you to actually put the point. A point technically is an X and Y value. Your book is a little lax on that. They'll say critical points when they really just mean X values, right? Or critical values. But what is my inflection point? I want to know the actual point through, where that concavity changes. Okay, I want to look at another one. Really quick, I just want to look at, let's look at really fast. One that doesn't change concavity. So for example, something like this. What if I had f of x equals, excuse me. Let's see, sorry. I'm having to overthink this a little too much. 3x squared minus x, something like that. So my graph is 3x squared minus x. Here's the thing, I know this is a parabola. It's pointing up, right? And it's scaled a little bit with that 3. Now, I don't know exactly where, I don't want to complete the square, so I'm not sure. I know it goes through 0, 0. If I put in 1, I'm at 2, right? And I could figure this out. If I put in negative 1, I'm at 4, so maybe it does something like this probably. But if I know kind of what the graph of this looks like, let's kind of hypothesize what I should be getting. Well, if you look at the graph here, right, it looks to me like we're concave up, we're C up everywhere, right? So let's see if the calculus actually supports my hypothesis. So, I don't know f double primed yet. What's f primed of x, right? That's 6x minus 1. Again, I'm not talking about maximums yet. We'll talk about that and how the second derivative can help us with that. But what is the second derivative of this function? It's 6. So where is 6? So do I have any inflection points? Remember, inflection points are going to occur where either my second derivative is 0 or where could I possibly change concavity? Where either my second derivative is 0 or my second derivative is undefined. In this case, my second derivative can never be 0 because it's 6. In this case, my second derivative can never be undefined because it's 6. So this guy is greater than 0 for all x, right? So what do we know about this function? This function is C up, right? This function is C up everywhere. So what do we know about an inflection point? We don't have any. No inflection point. I don't have an inflection point because I would have to change concavity, right, to have an inflection point. I have to go from concave up to concave down. Okay? I hope that makes sense. All right. What else did I want to show you? Let's look at one more. Let's see. How about this one? F of x equals x e to the x. Okay, so f primed, a little bit of product rule in the morning. It's never a bad thing. So leave the first derivative of the second, which is just e to the x, obviously, plus leave the second times the derivative of the first, which is just x. You could factor out that e to the x. Let's go ahead and do that because I know I'm taking the second derivative, so I don't know if that's going to help or not, but let's do it. F double primed of x then. What's the second? Again, I'm finding intervals of concavity. Leave the first. Plus, leave the first or the second, plus leave the second, derivative of the first, well, the derivative of x plus 1 is still just 1. Again, I can factor out an e to the x, right? So what would this, I'd be left with x plus 1 here. There's a 1 hanging out in here that we don't know about. So what is the second derivative? This is x plus 2, e to the x. So, all right, so let's see what we have here. Let me get rid of some of this. Get out of here, you boring quadratic. Quadratics are a bit boring when it comes to concavity. Wouldn't you agree? Poor quadratic. All right, so I have, this is my function. Remember, this is my second derivative, excuse me. What do I know about concavity? I know it's where it's positive and negative, and so I want to determine where is the second derivative 0, right? Because I want to know where it changes from being positive to negative or negative to positive. Well, e to the x can never equal 0, so e to the x won't contribute a possible inflection point, but x plus 2 can sure equal 0. That gives me negative 2. So if I test again at negative 2, so this is f double primed, right? I'm going to put in, well, and we can even, if you want to do similar to what we had done with the first derivative, I can test x plus 2. I can test e to the x. Guys, that's always positive, so you don't really have to test it. But then I can see what my second derivative is. If I put in negative 3 plus 2 is negative. E to the negative 2 is positive. So what do I know about my second derivative? It's negative, so I'm concave down. If I put in 0 plus 2 is positive, e to the 0 is positive, so my second derivative is positive, so I'm concave up. So where am I C up? I'm C up from negative 2 to infinity. Notice on all these intervals, when you're doing increasing and decreasing as well, and intervals of concavity, we always put open parentheses, okay? You're never going to be putting closed parentheses on these. Concave down, where we see down? From minus infinity to negative 2. And then sure enough, I have an inflection point. What is my inflection point? Well, it's going to be 2, comma, and then I'm going to put 2 back into the original function, right, to figure out what the actual y value is. So it's 2 comma 2 e squared. Let's look at the graph of this to see kind of what's happening. So I have y equals x times e to the x. Oh yeah, this one's really cool. So we set at negative 2, correct? That's where we had oh, negative 2. Oh no, did you see that, you guys? Negative 2, negative 2, negative 2, negative 2, don't mind me, negative 2, negative 2. What's the big, you know, negatives, not a huge deal, just totally changes your answer. All right, so if you look at this graph right here, I like this graph because it's not really clear to, it's not easy to see, I don't think, that it changes concavity, but this is kind of a gentle concave down, if I can use that word, right? The slopes are pretty flat, but if you notice, they're getting more negative, so negative, 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 getting more negative, not super negative. Then right here at negative 2, they start going more positive and more concave up. So concave up from negative 2 to infinity, and then concave down from minus infinity to negative 2. And that point right there, whatever that point is, right, negative 2, whatever, that's your inflection point. Nope, I don't want to do any of that. Okay, so what else can the second derivative do for us? So the second derivative can actually help us when we're wanting to find maximums and minimums, and that's going to be what we call the second derivative test. So let's talk about the second derivative test. So let's look at what so maximum, right? We know the definition of a maximum or a local maximum of a function. It doesn't necessarily have to be well, I guess I just drew minimum first, but it doesn't necessarily have to be an absolute max or min, but we know, what do we know about, we know a couple things, right, about a local max or local min. So at a local min, I know that the first derivative is 0, right, or undefined. Okay, we could have undefined also. But what do I know about the concavity? So we have this new exciting idea of concavity. So clearly, if you look at a function like this, right, if I look at the concavity of the function and I look at the second derivative, so there's the slopes of my tangent lines. Well, we can see that along this, whoops, sorry, I'm trying to grab a color I like. I shouldn't care about that so much. We can see in this function right here that I have an inflection point right here. And I can see that I'm concave up I'm C up on this interval, and I'm C down on this interval. So together with concavity and with critical points, if I can find a critical point and I can evaluate the concavity at that point, notice I have a local min, right, at that critical point when I am concave up. And when we're concave down, we have a local max at that critical point when I'm concave down. And so that's what we call the second derivative test. So sometimes the second derivative test works, especially if I have something like this, we're usually good to go. However, if I have something like that, right, if I have a cusp or a corner, I'm going to have some issues there because the first derivative isn't defined there, so the second derivative probably isn't going to be defined there either. I think I can even say it's not going to be defined there. So if I have a cusp or something like that, and clearly at this point, I go from being concave down to being concave down again, but here I actually have a minimum. So we have to be a little bit careful. So the second derivative test doesn't work all the time, but it is going to work on a lot of times where I have a function that's differentiable and it's not 0 at each place. So let's kind of state the second derivative test, and then of course I'm just going to do a bunch of examples for you. So theorem, I'm going to actually give myself a little bit more room. You know, sometimes you learn. Sometimes you learn, sometimes you don't. And this is called the second derivative test. Okay, so this is to find local max and mins. Second derivative. And this one, again, you can't have favorites, right? Right? But I kind of love the second derivative test. So let's let f double prime to be continuous. Okay, so the second derivative, right, exists and I have nice things going on. And let's say it is continuous on an open interval. Containing C. So I want to look around an interval around this critical point, right? And here's the other thing I need. I need C to be a critical point. So if C is a critical point, and we're going to say actually that not only is it a critical point, but it's a critical point such that the first derivative is 0. So remember, critical points can occur where the first derivative is either 0 or undefined. If we're using the second derivative test, I need it to be 0 because again, if I'm undefined, I have a cusp or something, and that's not going to work with the second derivative test, okay? All right, so a couple things here. First, if the second derivative at that point C is greater than 0, so remember if I'm greater than 0, then I am concave up. Remember that, I'm concave up. So what do I know? I know that at this point I'm concave up. I also know that I have a horizontal tangent. So what must we have there? We must have a local min. Then F has a local min. Can I just say min? And oh, I can say min, not mim. Min at C. Okay, that's all I have to show. So this is the nice thing with the second derivative test. I just have to show that it's positive at that number, and then I know it's a local min. I don't have to test around there. I know I'm concave up there. So likewise, if the second derivative evaluated at C is less than 0, so remember if it's less than 0, then I'm concave down, right? And there's my C right there. Then what is F going to have? F has a local max, okay, at C. And then what's the other option? Well, you guys, the second derivative could be 0. So the problem, I hate these little stipulations when I give tests, when we have tests like that. What this says basically is if the second derivative is 0 at that point, you don't know anything. Sorry, you're gonna have to go do something else. So I'm just going to put the test as inconclusive. So if that happens, and of course I'm going to show you one where that does happen, then we just go back to the first derivative test. Okay, we can always rely on the first derivative test to tell us these things. So let's do an example. I mean, what else are we going to do? We're gonna do an example. Let's do an example. So anytime it says, so I want you to make sure you understand, I will tell you which test to use. So I'll tell you whether or not to use the first or the second derivative test. And that is the test you shall use if that's what I tell you to use. So what are we gonna be using the second derivative for? You'll use the second derivative to find intervals of concavity, which I just showed you. That's when we're setting the second derivative equal to 0. finding intervals, testing around that number, finding intervals of concavity and possible inflection points. When we use the second derivative test to find extrema, local extrema, that's when we're using our critical points and putting them into the second derivative. So let's capitalize this because it's so important. Second derivative test, right? To find all local extrema of the given function. I'm not going to put that because I don't want to. All local extrema. All right, I plugged in my computer, so it's a little brighter now. Let's look at f of x equals 3x to the 4th. I think I've used this example before. I may have used it in the last lecture. That's okay. Squared plus 4. All right, so when you're using the second derivative test, the first thing you need are your critical points. So critical points, no matter what, are always given by the first derivative, okay? When do I set the second derivative equal to 0? I know I've already said this, but I'm going to say it again. I set the second derivative equal to 0 when I'm trying to find inflection points, not critical points, okay? So if we simplify this a little bit, I'm going to take a 12x out. I'm left with x squared minus x minus 6, I believe. So I have 12x times x minus 3 times x minus 2. Nope, plus 2. I got it. Plus 2. So what are my critical points? So my possible values for extrema are x equals 0, 3, and negative 2. Okay. So now that I have my critical points, I take the second derivative. So the second derivative, come up here, take the second derivative, equals what? 36x squared minus 24x minus 72. Okay, now I could factor out like a 12 and just leave it out front. As long as I don't factor out any positive or any negative number, it won't influence the sign of my derivative. So remember, all we care about is the sign of the second derivative. So now that I have that, now I just evaluate my second derivative at the critical points. If I put in 0 into this function, I get a negative 72. This is less than 0. It's negative, right? So remember, if it's negative, I'm concave down. This is what I always do because what I try not to do is memorize things too much, right? Try and think through it a little bit. If you remember that negative means you're concave down, I'll just like draw myself a little concave down and I'll be like, oh yeah, what does that mean? I have a local max, right? So we have a local max. And then I'm gonna test the other ones. F double primed of 3, that's 36 times 9, minus 24 times 3, minus 72. I get 180. Again, I don't really care about what that actual number is. What I care about is it's positive or negative. It's positive, so I'm concave up. So what do we have here? We have a local min. All right, and then finally, f double primed of negative 2, right, which is my other critical point, 36 times 4 minus 24 times negative 2 minus 72, I don't know, 120. Remember, these are just the values of the second derivative. This isn't the actual function values. These aren't not actually my minimum or maximum values, people, greater than 0. So I am concave up, so I have a local min. Aren't those great? And then you'll, of course, state those. So then you would state, you know, we have a local max of, what would I do? I'd put 0 into this function, so it looks like 4. Where does it occur? It occurs at x equals 0. And then I'll let you finish those, right? And then I have a local min of, not, these guys don't matter now, you guys. I just used those to determine if it was a local max or min. That is the only thing I used it for, okay? That's it. So knock it off. Stop. That's the only thing I used it for. All right, let's look at another one. So that was part A. I'm almost done, I promise. I'm not going to make this one, you know, the 50 minutes that the last one was. What about f of x? So let's look at one that was kind of similar to what we did before. Let's say x squared e to the x, okay? So f primed of x, then leave the first derivative of the second plus leave the second derivative of the first. If I factor out, let's see if I can, I'm just going to factor out that e to the x right now. And then let's see what's going to happen here. Okay, so now, remember, e to the x, that can never equal 0. Remember, I'm setting the first derivative equal to 0 because I want to find my critical points. If I set this equal to 0, I'm going to factor an x out. So what are my critical points then in this case? My critical points are x equals 0 and -2. Okay, so this is my first derivative. I'm going to come back to this. I'm going to find the second derivative, right? And sometimes the first derivative test is easier. Like if I were to do the first, I would probably do the first derivative test with this one because it wouldn't be too hard to test around 0 and -2. But you can't because I told you to use the second. And why might I do that? Because the second derivative is going to be a little bit, long, but that's okay. So we leave the first. We're not scared. Derivative of the second is just e to the x plus, leave the second, and derivative of the first. Derivative of the first is 2x plus 2 e to the x. And now because I know I'm plugging numbers in and I just want to make my life easier, if I factor out an e to the x and then combine the terms that are left, I just get this. And now even you guys, when I go to test my critical points, we know this is always positive. So actually I could ignore the e to the x. I'm not going to, just because I don't want you to get in the habit of that. And sometimes it's like, well, do I know that or do I not know that? But if I plug in 0, I get 2 times e to the 0. So this is 2, right? And that is positive. Therefore, it's concave up. So what do we have right here? We have a local min. Oh, yeah. I don't know why I'm excited about that. It doesn't really matter. What if I take f of -2? So I'm going to get, if I take f of -2 squared is 4. -2 times 4 is a -8 plus 2, right? Times e to the -2. So this is -2 e to the -2. Now this guy's always positive, so I have a positive times a negative, which is a negative. So that means I'm concave down, so I have a local max. Isn't that great? And these are so fun. I just love doing them. I think they're just a good time. And then of course you would state it, right? We have a local min of, well, if I plug 0 into this function right here, that's just 0. And it occurs at x equals 0. And then I have a local max, right, of, if I put -2 into there, I get 4 e to the -2. And where does that occur? At x equals -2. This is how you shall write your answers. I have said it. I have seen it to be good, right? And that is how you shall write your answers. I want to look at maybe one other example here. All right, one more quick example and then I'm done. I know, it's amazing. So let's consider the function f of x equals 3x to the 5th minus 5x cubed plus 3. So again, I'm going to take the derivative, first derivative, to find my critical points. So I get 15x cubed. This is a nice one, minus 15x squared. Let's factor out a 15x. Now, don't use, when I factor this out, oh, x squared, excuse me, right? Oh, that's a 4. Come on, Sarah. It's hard to subtract 1 sometimes. So I would get, what, x squared minus 1. So what are my critical points? What I was going to say is, don't you dare take the derivative of this, right? When we go to take the second derivative, you don't want to use product rule. My critical points then are, this guy's going to give me a -1 and 1, and this one's going to give me 0. So I'm going to put this in order, -1, 0, and 1. So let's look at the second derivative. So the second derivative, which I'm going to take from here, right, is 60x cubed minus 30x. And let's see what our second derivative is going to tell us. So my second derivative then, let's evaluate these. So at -1, right, I get a -60 plus 30, I believe, which is a -30. That is less than 0. That means I'm concave down, which means I have a max. Okay, f double primed of 0, though, my friends. 0. That makes me sad. That does not mean concave down. No. This means it's inconclusive. We'll come back to it. It'll be okay. Don't worry. Don't you fret. Okay, and then finally f double primed of 1 is just going to be 60 minus 30, which is 30, which is positive, which means I'm concave up, which means I have a min. All right, so these are going to be easy to find, right? I'm going to just take f of those values. and state my local max and my local min. So this inconclusive, don't fret. What I still have is I have the first derivative test. So if you get an inconclusive, you want to go back to the first derivative test and figure it out. Derivative. Because remember, I still know that I have a horizontal asymptote here. I just need to know does it go like this? Does it go like this? Does it go like this? I don't know. I just need to verify that. Maybe it's not a max or min, but I need to verify this. So what you have to be careful about this is I've already tested at -1 and 1. So I cannot go to the left or right of -1 and 1. So I'm going to look at f primed, right, at the first derivative test. So if I plug it into f primed into this guy right here, if I plug in a -1/2, this guy's going to be positive, right? If I take a -1/2, that's going to be like 1/4. And 1/4 minus 1 is going to be negative. So I'm going to have a positive times a negative, which is a negative. So I know I'm decreasing. And then if I plug in 1/2, right, I'm going to have the same thing. I'm going to have a positive here, 1/2 when I square it, right? It gives me another 1/4. And so this is negative. So at 0, there's no extrema. Okay, there's no extrema at 0. And the first derivative test has verified that. You need to verify that. You need to tell me, how do you know, right, that, how do you know that there's no extrema there? All right, guys, look at how cool this graph is. Isn't this a neat graph? So you can see we have our maximum at -1, like we saw. We have our minimum at 1, right? And then here at 0, I still have a horizontal asymptote. It's just really, really cool. It just, actually, it doesn't give me a max or a min. If I graph the derivatives, here's the derivative. I'm going to be done soon, I promise. I would just really like this one. So here's the derivative, right? Notice it is 0 at, oh, what did I do wrong, you guys? 15x to the 4. Oh, no, we're good. Yeah. I am 0 here at my maximum value, which is right there. Now, if I graph my second derivative, I want you to notice something. So if I do the second derivative, which was 60x to the third, sorry, I should have had this in there already, but you guys are used to me, right? And minus 30x. So I know this is hard to see, but if I graph the second derivative here, notice at 1, right, my second derivative is positive. And at -1, it's positive. And at 1, it's negative, which I don't think quite makes sense. Is that what we had? Yeah, at 1, no, at 1 it was positive. I'm sorry, you guys. Hold on. Yeah. I'm sorry. Anyway, you can see what's happening at 0 right here. I actually have an inflection point. So if you look at the green here, I'm 0 here for my third derivative, and I'm 0 there for my second derivative. Did I say third? I'm so sorry. It's been a long day of meetings. I should stop talking right now. Anyway, my first derivative is 0. My second derivative is 0 there. So that test is inconclusive. I hope that kind of makes sense. I hope I put in those numbers right. I think I did. But I feel like my second derivative at -1 should not be a positive number. Oh, it is a negative. I'm so sorry. I really need to stop being in meetings for so long. Here's -1. I was not looking at -1. And if you look at -1, the actual value of the green function is negative. I'm going to stop right now for the benefit of us all. Anyway, that's the second derivative test. It's a really good time. I think you would like it. I know you're going to, because I'm going to force you to do it. And of course, let me know if you have any questions.